at secondary calibration. We will look at secondary calibration for sensitivity. We will look for secondary calibration for frequency, and we will also have a look for secondary calibration for free-field calibrations of microphones. We will also have a look on low frequency calibration. Low frequency calibration is actually not described in the standard, but it might be a good idea to know how it can be performed. And then I will show a demonstration of the grass microphone calibration system. It will take about 10 minutes. And in the end, there will be time for some questions. For questions, please use the Q&A function in this webinar. You can find the Q&A functions in the upper right corner of your screen. Introduction to calibration. For making documented, traceable, and approved measurements, your measurement equipment must be calibrated. Calibration is a method for establishing a relationship between a measurement device and its measurement units. Let's have a little example. 1 meter. If we would like to calibrate a ruler or something like that, then it will be calibrated up to the standard for 1 meter. And the standard for 1 meter is actually defined as the length of a part traveling by light in vacuum in 33 nanoseconds in this neighborhood. When we have actually established the relationship between the ruler and the described standard, then the ruler is actually calibrated, and we can actually trust the data for this ruler, and we have in this way a reliable measurement with our ruler. So calibration is a method that establishes the relationships between the measurement device and its measurement unit. And this is done by comparing a device or the output of an instrument to a standard with a known characteristic. What is acoustical calibration? Calibration means comparison of values indicated by a measurement instrument with a nominal value that is provided by a given standard. As we saw before with the ruler, when we are talking about acoustical measurement, then we are our standard is actually pressure, normally pressure in Pascal we are looking at. The equipment used for the calibration must itself be suitable, calibrated to ensure an unbroken trace back to the standard kept at a national or international institute. So the equipment we are using for doing calibration must be traceable back to a given standard, either at national plan or international plan. Quality in your measurement. For performing a quality measurement, you must keep these factors in mind. First of all, resolution. Does the instrument meet the requirements for the application for what you would like to measure when we're talking about resolution? Accuracy. Does the measurement reflect the true characteristics of what is measured? And third, precision. do you get the same result each time you measure the same quantity? So the total accuracy of the calibration needed is directly dependent on these considerations, the three considerations we have here on this slide. How often should I calibrate? It's actually a question coming up very, very often. How often should we actually calibrate our microphones, our equipment? And it depends on the types of measurements, as well as the quality assurance systems you have, and the quality assurance system you would like to follow. Below, I will give you some guidelines to determine when calibration is needed. When you receive a new instrument, when you receive a new microphone, a new analyzer, whatever it is, then it's actually a good idea to start making a calibration of the new unit, to ensure that the new unit is fulfilling its specifications and also fulfilling the requirement for the measurements you would like to use it for. When a specific time period has elapsed, it could be 1 year, often it is one year, then it could be a good idea to perform a new calibration of your equipment. When a specified period of usage has elapsed, operation hours has elapsed, then it could be a good idea to do a calibration. When an instrument has been exposed for extreme environmental changes, it could be changes in temperature, humidity, static pressure, that might have affected its performance, then it's also a good idea to perform a new calibration. And when an instrument has been subjected to shock or vibration that might have affected its performance, then it's also a good idea to do a calibration. And whenever measurement results appear to be questionable, then it's also a good idea to do a recalibration of the instrument. Why should we calibrate? Yeah, first of all, it could actually be to fulfill of externally requirements. It could be legal requirements because the measurements you are performing has to be according to certain standards and legal standardizations. It could be due to if you have to fulfill some standards. It could be you would like to fulfill internally policies. It could be the company's quality assurance policy. It could be internally described policies. And of course, you also have to ensure that you are doing the correct measurements. So calibration will give you confidence in your measurements. The calibration pyramid. For many of you, if you are a user of an instrument, then you are in the lowest part of the calibration pyramid, where you are working with what we call a working instrument, an instrument you are using in your production line, you are using for doing verification and validation measurement in R&D and things like that. These instruments you will often have these instruments calibrated, and in many cases you will actually do an accredited calibration of these instruments, and accredited calibration up against a working standard. The instrument use for doing calibration for the working standard, they have to be reference instruments, so they need an accredited calibration, a calibration with a better or a more accurate uncertainty budget. Or the accredited calibration instrument, they are calibrated up against a reference standard, the secondary calibration. And if we go up to national or international plan and international standards, then we are talking about primary calibration, which only are carried out a few places all over the world. Many countries might have one institute in their country where they are able to do primary calibration. In this webinar, we will actually cover from working instrument up to secondary calibration. We will have a little look on primary calibration, but the main focus in this webinar is secondary calibration. So we have to have a look at the microphone measurement microphone standard, the IEC 61094. This standard consists totally of 8 chapters. 2 of these chapters describes the specifications for the microphones fulfilling the standards. It's part 1 and part 4. Part 1 describes the specifications for laboratory reference microphones, the reference microphone you normally are using on secondary as well as primary laboratories. And then we have the IEC 61094-4. This is the specifications for working standard microphones. Actually, most of the microphones you are using in production lines, in R&D, actually using everywhere for doing sound measurements or noise measurements. For doing calibrations of laboratory microphones, laboratory reference microphones, then the standard has actually the part 2 and 3, which actually describe how to do calibration of primary microphones. For doing calibrations of working standard microphones, we do have part 5. This is the pressure calibration. We have part 6, which is the electrostatic actuator calibration, and we have part 7 or 8. Sorry, part 8, which is a method for finding the free field or doing a free field calibration of a working standard microphone. So in this webinar, we will actually mainly concentrate on part 5, part 6, and part 8. But before we do that, then I think it's a good idea to have a little look at the primary standards, actually part 2 and part 3. But before that, then a little description of the measurement microphone standard. As mentioned, the specification for microphones fulfilling the measurement standard, then part 1 and part 4 is important because these 2 parts describes the specifications. Part 1, the specifications for laboratory microphones, and part 4 for working standard microphones. Laboratory microphones, as we have it here, LS2P, LS means laboratory, L means laboratory, S standard, 2 for a half-inch microphone, and P is actually the type of microphone. It's a P for pressure microphone. In the standards, both part 1 and part 4, there's a lot of different parameters the microphones has to fulfill. It's parameters like sensitivity, it's parameters like frequency response, dynamic range, size, environmental parameters, static pressure, temperature, humidity, stability, both long-term and short-term stability. Laboratory reference microphone glass are producing one called 40AU-1, and this microphone fulfill all the listed requirement according to the standard. Working microphone. WS mean working standard 1 for 1 inch, P for pressure, 2 for half-inch, P for pressure, F for free field, and D for diffuse field. WS3 for quarter-inch, P for pressure, F and for free field, and D for diffuse field. It's the working standard microphones. It's all 1 inch, half-inch, and quarter-inch measurement microphones. 1/8 of an inch is actually not described in the standard, but the 1/8 of an inch microphone available on the market, they are all made according to the standard. It means you would have the same type of specification for the microphones, and the microphone will also have a size which actually is in accordance to the standard. All measurement microphone has, as the laboratory microphone, a huge range of specifications you have to fulfill to be able to call it a standard measurement microphone. If we look at primary calibration, primary calibration, then we actually are talking about the IEC 61094-2, the primary methods for pressure calibration, reciprocity measurement. And the principle is we are doing a pressure calibration, and the pressure calibration is done in a coupler where we have a reference microphone and we have the microphone we would like to calibrate the device under test. It's placed in a coupler. We can also do this test in a free field calibration where we put the two microphones in a little acoustical chamber or an anechoic chamber, and like we have here on the picture. And then the idea with the calibration is that we will first of all actually use the reference microphone as a transmitter, and afterwards as receiver, and the same actually with the microphone on the test. And in this way we are able to obtain the to measure very, very precise the sensitivity of the microphone. And as mentioned, reciprocity measurements is mainly used in primary laboratories. Part 7, values for difference between free field and pressure sensitivity levels of laboratory standard microphone. And it's actually a description how to describe and how to compensate, to correct for the difference between a free field microphone and a pressure microphone. Part 5 is actually the part describing the pressure calibration or the sensitivity calibration of a working standard microphone by comparison method. There are different methods we can do that. We could, like we have it here on the slide here, we could have a little sound source, and we could have a coupler with a cavity, and then we could have a reference microphone and the microphone under test. And the idea is that these two microphones, they will see the same pressure from the little sound source. And if we have a reference microphone where we know the sensitivity and what it is measured, then we will actually compare it to what we actually see from the microphone under test. The principle of a comparison method is that the reference microphone and the microphone under test is simultaneously or sequentially exposed to the same sound pressure level as we saw on the little drawing. Comparison, we can do the comparison with a reference microphone. A reference microphone calibrated at a reference laboratory. We can also do the comparison with a piston phone or a calibrator, also calibrated at a reference laboratory. Coupler with microphone and sound source. We can make the setup with where we are using a microphone as a sound source, and then we have our reference microphone and the microphone under calibration or under test close to each other. So in this case, they will see exactly the same sound pressure level. By this, we are actually also able to do to calibrate at different frequencies from in the neighborhood from 20 hertz to 20 kilohertz, and we are able to obtain a level of around 100 dB. We can also use a coupler with a speaker as a sound source, as we saw on the previous slide. Here we are normally able to obtain a frequency from 250 hertz to 16K, level from about 70 dB to 110 dB. And then we have the piston phone. The piston phone is a very precise sound source made on volume displacement, where we have inside the little chamber, we have two pistons or some pistons. These pistons will move due to the cam disc here will turn around, and it will start making these pistons moving. When this piston is moving, then we will build up the pressure inside the chamber. The piston phone is a fixed frequency, normally 250 hertz. Level, it could be 94 dB, it could be 114 dB, or even higher, 134 dB. 114 dB is more or less standardized. We will have a closer look at the piston phone. So let's look here at next slide. The piston phone is a very precise sound source, as I mentioned. It's based on volume displacement. We talked about that before. It's geometrically, we have to make a geometrically control of it because depending on the atmospheric pressure, then we have to compensate for the atmospheric pressure. So the level inside the chamber will be a little bit more, a little bit less, depending on the atmospheric pressure. but it's a very linear curve, so it's rather simple to do the corrections. The frequency is 250 hertz, or if we would like to be very precise, then 251.2 hertz, 251.2, due to we are talking about the center frequency of a 1/3 octave filter, 250 hertz filter, which is 250.2 hertz. Very precise, 114 dB equal to 10 Pascal. If we look at the we could also use a sound calibrator. So let's have a closer look at the sound level calibrator, like the Grass 42AG. The principle in a sound calibrator is that we have a little speaker, which actually will build up the correct sound level inside the coupler. And we have a pressure sensor, and the pressure sensor will actually measure the actual pressure inside the coupler, and then it will actually compensate. So we, in this way, will have a closed loop. So we have the right level inside the coupler. It could be 94 dB, it could be 114 dB, or another value depending on type of calibrator. The calibrator do also measure the atmospheric pressure, and therefore we are actually compensating in the sound, in a sound calibrator, for the atmospheric pressure, so we don't, as a user, have to think anything about if it's if the static pressure is high or low. We just have to add the calibrator. The Grass 42AG is a high precision, multifunction, and easy to use sound calibrator. It conforms with the standards for calibrators and piston phones, the IEC 60942. Special with the 42AG is that you have a dual frequency, so you actually have the possibility for checking a little part of the frequency linearity of your microphone, as we have 250 hertz and 1 kilohertz. We have also dual level, so we have the possibility for checking the linearity of the measurement chain. Dual level is 94 dB and 114 dB, 1 Pascal and 10 Pascal. As an extra plus, you will also have the environmental parameters for documentation of your measurements. So you have air pressure, you have temperature, and you have humidity in the little device itself. If we compare the sound level calibrator up against a piston phone, let's first have a look at the sound calibrator. The sound calibrator is for verification of your measurement chain. So a sound calibrator is a verification instrument. A sound calibrator is for field use, for daily use. To be used with all standard measurement microphones. It can be used together with low noise microphones in the mode 94 dB. You don't have to make any corrections for the static pressure. No correction for the microphone front volume. You have to correct when you are using a 1/2 inch free field microphone, then you have to correct the level a little, due to the free field microphone will start, the pressure field will actually start falling off with about minus 0.15 dB at 1 kilohertz. So you only have to correct at 1 kilohertz. If you look at the piston phone, The piston phone are for calibrations of microphones and microphone sets. It's for laboratory use. It has a very high precision, standard, plus minus 0.8 dB. With an accredited calibration, you can actually obtain a better uncertainty on plus minus 0.5 dB. You have to correct for the static pressure, and you also have to correct for the front volume of the microphone. So the sound calibrator, it's not for secondary calibration laboratory. It's only or more for daily verification of your measurement chain and your microphones. While a piston phone is for secondary calibration laboratory. So the calibrator is something you are using in the field for verifying that everything is working correctly, while the piston phone is something you are more using in your laboratories. Let's have a look when we are doing calibrations of microphones. See a microphone, the capsule itself, only the capsule. If we are looking at the capsule, then on the calibration certificate of the microphone capsule, then you will find the open circuit sensitivity. And it's actually the sensitivity of the microphone capsule without the load of a preamplifier. So we don't have a preamplifier mounted. We don't have the gain from the preamplifier. It's for the capacity of the microphones only. The closed circuit sensitivity is actually the output of the microphone when the microphone is mounted on a preamplifier. And that's actually the closed circuit sensitivity is actually how we normally will use a microphone. And that's also how you, when you are doing measurement in your production line, in the field, community noise measurements and things like that, then it is as a closed circuit sensitivity. The closed circuit, and we can calculate this closed circuit sensitivity because it's actually, if we look at the diagram we have here, Cm is the capacitance of the microphone, while the Cs is the input capacitance of our preamplifier, and there will be a voltage division between the microphone capsule itself and the capacitance in the preamplifier. If we calculate this, then we will find out that for a standard half-inch microphone, then the closed circuit sensitivity is about 0.2 dB lower than the open circuit sensitivity is. But how do we actually measure the open and closed circuit sensitivity? The open circuit sensitivity is for the microphone only. It's independent of preamplifier. It's a standardized value because this is actually the value measured or mentioned in the IEC 61094 standard. But it's actually not a very practical value because you as user has to compensate and calculate every time you mount actually a microphone on a preamplifier. But it's a part of the IEC standard. The closed circuit sensitivity, it depends on preamplifier. It's not a microphone parameter according to the IEC standard. But it's very practical value because it's actually the value indicated what you have on the output with a certain input on your diaphragm. Let's have a look how this actually is done, how we actually measure the open circuit sensitivity. The open circuit sensitivity is normally measured together with a piston phone. It's measured together with a special amplifier. We call it a insert voltage amplifier. And when we are using the insert voltage amplifier, then if we look at the picture we have down here, in a insert voltage amplifier, we have the possibility for having a generator signal, a voltage input to the amplifier, so we can actually put in a voltage to the amplifier, actually a voltage where we are using the microphone as an input capacitor. But let's have a closer look on this. When we would like to find the open circuit sensitivity of a microphone capsule, then first of all we will switch on the piston phone and then measure the output of our preamplifier on which we have mounted our microphone. So the microphone will actually work as a standard microphone. It will obtain the pressure and give us an output voltage, and this output voltage can be measured on the output of the preamplifier as VO. In next step, then we will actually switch off our piston phone, and now we will switch on the generator. So now there will be a signal from the generator going in, this to the via the preamplifier. We are wiring the preamplifier, and it will actually go directly to the microphone capsule. Via the preamplifier, and now we can actually start measuring. So we know the generator here. The level from the generator is called V1, and the output is V2. And what are we doing? We're actually trying to adjust V1 until the output is equal to what we actually measured before, just with the piston phone. And when we have done this, when V0 is equal with V2, then we can actually measure V1 with a voltmeter, because V1 is actually equal to the open circuit sensitivity, is actually equal to what the microphone is looking at, the sensitivity or the pressure level the microphone is looking at the diaphragm. A typical setup for this, where in this case we have used an AP, audio precision analyzer, a glass power module with insert voltage possibility, and an amplifier with insert voltage and a reference piston phone. And in this way you are able to obtain the insert voltage according to the procedure we saw on the previous slide. When we are making microphone calibration with our piston phone, then the piston phone level, it must be corrected for, first of all, the atmospheric pressure, and the value we have to compensate is easy to calculate. It's actually just the logarithmic between the relations between the actual pressure and the reference pressure, 1013 hectopascal. Next, we have to know the front volume of the microphone, and when we know the front volume of the microphone, then we can also calculate the piston phone level when we have made the corrections according to the formula given here. If we look at microphone sensitivity, then the standard describes that the microphone sensitivity has to be measured in millivolt per Pascal or in dB relative to 1 volt per Pascal. So we actually have to do both measurements, and yeah, it is actually just a calculation. So normally we will measure the sensitivity in millivolt per Pascal and use the formula here. And then when we have found the sensitivity in millivolt per Pascal, then it's easy to do the calculations relative dB relative to 1 volt per Pascal. We also have to look at uncertainties and uncertainty budget for our microphone calibrations. If we look at the uncertainty chain, then it's a long chain of different uncertainties. First of all, we have some uncertainties for the reference microphone. The microphone might create some distortion. It will create some uncertainty. We are also using a piston phone. There are also some uncertainty or stability of the piston phones. Then we have to compensate, or we will have some uncertainties if we change the temperature for the calibrations. We also have an uncertainty on the static pressure corrections. We have an uncertainty on the humidity, how much the humidity is deviation. And then, of course, we have in the end uncertainty on the instrument, the voltmeter we are using for doing this measurement. All these uncertainties, they are added into a formula. So we take the first uncertainty and multiply it by a weighting factor, and then take the square of that, and then we add the next one until we have all the uncertainties. If we do calculations for this, then we also have to remember the expanded uncertainty. So we have an extra factor, this is 2. And then in the end, we can actually do a table and find the totally uncertainty. If we do these calculations with a standard glass calibration system, then for the level calibration, then we will end up with an uncertainty of 0.073 dB. Frequency calibration. Frequency calibration, according to IEC 61094-6, is where we are using an electrostatic actuator for finding the frequency response. For doing that, we need a generator and an analyzer. We need an electrostatic amplifier able to provide a high DC and also a very high AC signal. And then we need the little electrostatic actuator itself. Let's have a look on the principle in the electrostatic actuator. From the generator, we will have our signal. It could be from 100 Hertz, maybe 20 Hertz, up to 200 kilohertz, depending on microphone under test. We have an AC amplifier. This AC amplifier will create, so we have maybe a 100 volt RMS. We will also have a DC supply, normally an 800 volt DC supply. The 800 volt with the 100 volt excitation signal will go to the electrostatic actuator. Then we have our microphone under test and a preamplifier, and then back to an analyzer. So we actually are able to make a frequency response. If we look at the principle in the electrostatic principle, then the actuator itself, it will actually, the plate there will actually be parallel with the microphone diaphragm, and it will therefore create a capacitor between the microphone diaphragm and the plate. So if we are actually adding a capacitor in the top of the microphone, so to say. Between the capacitor plates, the actuator plate itself, and the diaphragm of the microphone, we actually produce a force which actually will make the diaphragm moving. This force or pressure is frequency independent, as long as we apply an AC, as long as the applied AC and DC voltage are kept constant. We can do some calculations, but what's more important is if we keep the 800 volt constant, then the pressure levels we are able to obtain is, if we have 100 volt AC over our actuator, then we are able to build up a pressure equal to 2 Pascal, 100 dB, 70 volt 1.4 Pascal, 50 volt 1 Pascal, and 30 volt about 0.6 Pascal. The actuator methods can be used in a huge frequency range, actually from 20 hertz up to 200 kilohertz. I had to say, when I say 20 hertz, then the IEC standard describes that you can use it from 100 hertz, and I will come back to that. As the pressure the actuator produce on the diaphragm is frequency independently, we would assume that the pressure response measured by the microphone is flat, is ideal, but the measured result deviates a little from that. Deviation is actually due to that a small additional pressure is generated due to the movement of the diaphragm. So when the diaphragm is moving, then you will build up a resistance, mainly at higher frequency, which will give a little less sensitivity of the microphone at the higher frequencies. The actual response measured with an actuator is pressure. Free field, with free field, we have to do a random incidence field. We have to apply some correction factor to the actuator response measured for finding the free field and the random incidence response. So when using actuator, we have to measure the actuator response, and then we have to do some corrections upon on the top of that. If we look at low limit of frequency, the actuator method cannot be used down to approximately 5 to 10 times the lower frequency cut off of the microphone. And I have to mention that the standard specified 10 times. For some microphones, you can actually use it out to 5 times. And this is actually due to that the electrostatic method, it will not excite the venting system of the microphone capsule. and it means that at low frequency can be see it as a reduction in the total stiffness of the microphone capsule, and therefore the microphone capsule will actually be more sensitive at lower frequencies if an actuator is used. Let's have a closer look at that. We have here an actuator response at low frequencies. The blue curve is the actuator response. The green curve is actually the right response measured for that microphone. Theoretically, if we measure with an actuator, then we will actually see something like the dotted line here, a more flat curve at lower frequencies. We do not see that, and it's actually due to we have some other small issues when we're doing these measurements, and it is that we have a cutoff frequency of our electrostatic amplifier and also our microphone amplifier, so we will not see this really actuator response. But what this graph actually tells us is that we aren't measuring correct at lower frequencies. I will come back to low frequency calibrations in a few slides. Actuator frequency response uncertainty budget for microphones. It is exactly the same methods as we saw before for level calibration. We have to add all the uncertainties. We have to add, put in a weighting for these uncertainties, and then we have to calculate the totally uncertainties. If we do that, then we will end up with, when using actuators, an uncertainty on 0.2 dB in this neighborhood. Measurement microphone, the free field calibration of working standard microphones, done by comparison, where we have the test microphone and a reference microphone. So we are comparing our test microphone up against a reference microphone. There are actually two methods: basic substitutions calibrations done in a free field chamber and an anechoic chamber, or time selective principle. Let's have a look at these two principles. If we look at the calibrations, comparison calibrations done in an free field in a chamber, sound source, then we need a sound source. The sound source could be a speaker or a microphone. The reference microphone is actually a microphone where we have a very, very well-known frequent free field response. And then we need, of course, our microphone on the test. The procedure is measure the free field response for the reference microphone, mount the microphone on the test in exactly the same position as the reference microphone was mounted in, and then measure the response of the DUT. We are actually assuming that the acoustical sensors for the two microphones is in exactly the same point. The sound field remains the same, and then the free field sensitivity or response is fine from duration of the dot and the output of the reference microphone. Time selective principle. We also here need a sound source. It could be a speaker or a microphone. We need a reference microphone, also with a well-known free field response. We need the DUT. And the idea here is that we don't want to look at the reflecting sound. So we will actually only look at the direct sound. So we will actually only look at what we actually receive from the direct port here. And this is actually done by having an impulse from our sound source, and by only looking on a little part of the time signal, the first few seconds, then we will actually be able to obtain the true response for the microphone under test. Because we are looking at the reflections, so we will actually get rid of all the reflections. A measurement setup for this could be something like that, where we are using one of our AP analyzers, and it's an analyzer with software for calibration of free field in a free field chamber, frequency response measurements, or we can also use it for time selective measurements. Reference microphone and DUT. Low frequency calibration. For calibrations below 5 to 10 times the lower frequency cutoff of the microphone or microphone set, we can't use an electrostatic actuator. A piston phone principle can be used. Actually, a principle like this, where you have a speaker, you have an amplifier to this speaker, and you have a coupler together with the speaker, and then you would actually use the speaker, the diaphragm of the speaker, the cone of the speaker, as to act as a piston moving up and down. By doing this, you have the force to the speaker, and we know the magnetic field in the speaker. We can also adjust or measure the current, and by this we are actually able to calculate the force, and therefore finding the pressure inside the chamber. To measure accurate, then we might or could eventually have a reference pressure sensor. We have, when we are doing calibration like this, then we have to ensure that the venting system of the microphone under test is venting into the coupler, because otherwise we will only see the difference between the pressure inside the coupler and the atmospheric pressure we have outside the coupler. For calibrations of microphone capsules, it is recommended to use a preamplifier with an extra high input impedance, first of all, to avoid conflict between acoustical and electrical cutoff. Of course, it doesn't matter if it's a microphone set, a combination between a preamplifier and a microphone capsule, because then we can consider it as a system. But so only if we are only calibrating microphone capsules, then we have to use a preamplifier with an extra high input impedance. If we look at equipment available for calibration, then we have the GRASS 42AG. It's a multifunction calibrator for sensitivity calibration in the field. The GRASS 42AA, 42AP, 42AC, the piston phones, also for sensitivity calibration, but sensitivity calibration in laboratories. 51AB, it's a two-port calibrator. It's a two-port calibrator which actually can be used for comparison calibrations for finding the sensitivity, frequency, and sensitivity. The GRASS 42AE, low frequency calibrations for calibrating of microphone capsules, low frequency sensitivity, and low frequency calibration. The 14AA, the electrostatic actuator amplifier from GRASP for frequency calibration, the RA14, the electrostatic actuator, and then we also have the 19CA, the microphone calibration system, which actually can calibrate, both sensitivity and frequency response. I know I have actually used 1 hour, and I have a demo now. It's 10 minutes for the one of you who would like to see this demo. So I will start the demo. See, when you start up the system, then the first thing, of course, you have to put in is the operator, who you are, who is doing the test. You have also to put in the barometric pressure, today's pressure. This is actually normally read directly from the piston phone. You have to put in the temperature, calibration temperature, and you have to put in the humidity. When you have entered all the test conditions, then you say, okay. And now we are ready to measure or do a calibration. So we start new calibration. And when we are in new calibration, then we have type of calibration. We can actually, with the system, calibrate microphone capsules, which we have selected right now. So that's a long list of microphone capsules. We can also calibrate microphone sets. There's also a very long list of microphone sets. We can also do calibrations, random combinations, where we have a microphone capsule and a preamplifier, and we have mounted these two together, and then we will calibrate them as a set. So we only have one sensitivity to use. But what I have here is a microphone capsule. It's actually a GRASP 42AG. It's a pressure capsule. So I will select the 40AG. I will put in the serial number for the 40AG I have selected. I have also in the system possibilities for adding a customer ID. It could be an address, department, whatever. I can also select which frequency I would like to start at. In this case, I will start at 20 Hertz. So we can see the test conditions are in the system, and also all the data for the microphone I would like to calibrate. So I will start with a level calibration. As you can see, there are actually two level calibrations. There's one called level calibration and the other one called level 2. Level 2 is if you would like to have the calibrations done on another frequency. It could be 1 kilohertz, where you are maybe using a GRASP 42AG for just testing the level at 1 kilohertz. But I will do a standard calibration with a piston phone at 250 Hertz. So I have started it up, and now the microphone is actually warming up and we can see that the pressure is slowly built up. And the reason why it takes a little while is it's an externally polarized microphone, and the polarization voltage for the microphone has to be built up. We have actually to charge our capacitor in the microphone with the 200 volt, and it takes, of course, a while. Now we can see it's more or less stable. What I did here before was actually I was knocking in the table, and it was actually for showing you that I have two graphs. I have the white graph, which is the instantaneous graph, and I have a red one, which is an average measurement. When these two are equal, then the green stable indicator will light up, and we are actually ready to go to next step. This was a microphone capsule, so we had to do this insert voltage calibration. We have to find the open circuit sensitivity. So now the first part, we added the piston phone, we made the reference with the piston phone, and the second part, we actually apply and adjust until we measure the same. And now we actually have found the sensitivity. We have both the sensitivity in millivolt and also in dB relative to 1 Pascal. The frequency, we also have the deviation between the nominal value and the measured value. Next step is actually frequency calibration. So we will press the button frequency calibration. Hey, it looks like the little video here stopped. In frequency calibration, when we start it up, then we can actually see that the frequency starts sweeping. And if we look at the graph here, then we can see we actually have it is failing. We have some issues in the lower part. We have also some issues in the upper part. And the first time we are running it, then it's actually due to the polarization voltage is not up running. Now you can see it's much better. It's actually okay in the center part, but we still have issues in the lower part. And it looks also that we have some issues in the upper part. The lower part here is actually due to we have a 20 Hertz filter in our power amplifier, in our microphone amplifier. I will switch this one off and try once more. And now we can see that it's actually okay at low frequencies. But we are still touching the right corner up here. And that's actually due to it is one of my demo microphones. So I have dropped this microphone a couple of times. So therefore it is failing in the upper end. So I will just accept this and say, okay, I know that the microphone is not perfect. It's a little bit out of tolerance at the high frequencies. So I have a green light for sensitivity. I have also done the frequency response. So what next step is I will save the data. And now I have actually saved a raw data. I will also print a calibration certificate. It's a printed certificate in PDF. You have actually as the possibility for designing the certificate yourself, so you can build it up with logo and the information you would like to have on the certificate. I've now done the calibration, and I can, if I would, I can do an analysis of the result. So I can see the whole frequencies, and I can see at 20 kilohertz, I'm actually touching the tolerances a little. So it's maybe 0.01 dB out at 20 kilohertz. So it is actually nothing. In the microphone definition picture, I can see all the equipment I have used for, or the coupler I have used for the calibration. how the coupler is configured, the level of the coupler on piston phones, and also upper and lower uncertainties, limiters, and things like that. So I have a good picture of what we actually have done. In the under definition, I can see the type of microphone I have calibrated, and size, type, pressure microphone, polarization, voltage. I can also see where I will save the data for this calibration files, both the raw data, as I call it, and the calibration certificate, and where the system is actually finding the configuration of the certificate. And then we actually have the limits and what we have measured at the different frequencies. And then we have a list of all the equipment we have used, and also the traceability back to the system. This was a little tour in the GRASS microphone calibration system. So, questions in what we actually have been through. But before we go through the questions, then yeah, you can actually also you can send an email directly to me, or you can use our support email if you have questions. But let's have a look if there are any questions in the chat. Questions down here. And here's a question. Is the pressure correction for piston phone valid down to, let's say, 80 kilopascal? Yes, it is. You can actually use it down to about 700 and up. Does the open circuit sensitivity of a microphone always stable in time? Yeah, it depends on what you actually are meaning with in time. The open circuit sensitivity, as you saw, if you saw the demo system, then there's a time constant from when you actually apply the polarization voltage until the microphone is 100% stable. It's about 30 seconds. So an externally polarized microphone, when you start doing calibration, then wait about 1 minute after you have applied all the supply voltage to the microphone before you actually do your calibration. Is calibration according to part 8 also possible in a diffuse field instead of a free-flow anechoic chamber? Yes, if you use the time selective calibration methods. And here, do you have solutions for calibrations of sound level meter with free field, or I think it's sound level meter in a free field? We do not have turnkey systems for that, but our analyzers can actually be used, but we don't have a complete system for doing free field calibration and not free field calibrations of sound level meter. And here it is mentioned that the frequency response for this calibration should be from 20 to 20 kilohertz. But the answer is the same. We can use our equipment. If you would like to set it up yourself, we don't have a complete solution. What is the advantages of using a microphone as a sound source over a loudspeaker? The advantage is that the microphone is actually very linear. It will actually produce the same level at all frequencies. A speaker, of course, you have a lot of unlinearity in the frequency domain. I think this was actually the questions. I will wait a little, and when I'm waiting, if there is any more questions, then I can actually say I hope to see you again on one of our next webinars. Actually, we have a webinar again on the 17th of May. It's an AP webinar where we are talking about the big 6 measurements. It will be on the 17th of May. We have another webinar on the 7th of June. It's smart speaker measurements, and this webinar is a joint webinar between grass sound vibration and audio precisions, where we will talk about grass and audio precisions instrumentations for test of smart speakers. And now here's another questions about my questions about stability of an open circuit sensitivity. I meant an older microphone. I meant an older microphone of 20 years can be used with the labeled sensitivity. Yes, I mean, you can use a very old microphone as reference microphone, as long as you actually have reference for this reference microphone. And with reference, I mean, if you have a yearly calibration of the microphone, then the microphone is still valid. No doubt about that. And then there's one here, he would like to have an example of the microphone calibration certificate. We will send this sample to you via the system. I can actually say that the webinar here, we will also send a recorded version to all of you here within a week, and together with that we will send some examples of the calibration certificate from our system. I think this was actually the questions, and this was actually the words from today. Thank you for participating, and I'm sorry that I was using too much time, but I do hope you gain something doing this presentation. So thank you, all of you, and thank you for participating.